Okay, well, let's see some of this organometallic chemistry in action. So let's start with a nice simple halide. Not because halides have to be simple, but because it's easy to draw and quick to communicate. Okay, so let's take a halide, react it with magnesium in a solvent like ether, and that's going to form our organometallic reagent. This is our strong nucleophile. So, what are we going to do with our strong nucleophile? Well, now we're going to react it with a carbonyl compound. Now note, this requires separate steps. So the first step, we're going to make the Grignard reagent. Once the Grignard reagent is complete, we're going to do step 2. And step 2 could be adding a weak electrophile. So these happen sequentially in time. We first mix the magnesium with the methyl bromide to get our Grignard reagent. Once it's complete, then we will introduce the electrophile. So we won't have everything mixed together at once. We will control the order in which these steps occur. So now our strong nucleophile is going to attack our carbonyl. This is our nucleophilic addition. This carbon the carbonyl has 4 bonds already. If we're going to make a new bond to it, we need to break an old one, and that breaks that CO pi bond, pushes the electron density up on the oxygen. Now, this gives a new species. This carbon has gone from being sp2 hybridized to sp3. And now it's a tetrahedral carbon. Oops, can we go back on that? Yeah. And we call this a tetrahedral intermediate. We will refer regularly to tetrahedral intermediates. If you want to be fancy, you can put in brackets, but I'm normally not that fancy. But it's a tetrahedral intermediate. Tetrahedral intermediates can do 2 things. They can lose a leaving group, which we're not going to see for a while, or typically these days, we are going to have a proton source. We're going to protonate this O-, and that's the way we're going to neutralize our product. Now, this requires a third step. We're going to add water. Now, we don't want to add water early on, so we have to hide the water from the reaction until we're ready and we formed our tetrahedral intermediate. And how do we communicate that? Well, we number the steps, saying, don't add the water until step 2 is complete. So the O- will deprotonate that water. And we get, this is our product. We get an alcohol. So, where did this alcohol come from? That alcohol oxygen came from the carbonyl. Whoops, and I'm messing up my thing, but that oxygen came from the carbonyl oxygen. And so we've added something to the CO pi bond. We've added a methyl group and a hydrogen. So this is a nucleophilic addition. There are a lot of ways we could write this. We could write this all in one reaction, all on one arrow. So to condense it, okay, step 1, we're going to treat with magnesium and ether. Step 2, we could add the carbonyl, and then step 3, we'll add water, and that will give us our product. So we don't always have to show all the intermediates. Sometimes we just have to show the reagents. And if the reagents require steps to be numbered, we need to number them. Note that anytime you number something, you're not saying how many ingredients are in there. You're saying the order in which the ingredients are added. You wouldn't number magnesium 1 and ether number 2. They're mixed together. They are all part of step 1. How else might you show this? Well, sometimes people emphasize the carbonyl compound. So say, okay, I want to treat this carbonyl first with methyl magnesium bromide. So we're sort of skipping the step that we actually had to make our Grignard reagent. And step 2 is with water. And that gets us to our same product. So there are different ways to represent this, but we're all communicating the same thing. Note that the top process, we're really highlighting the mechanism. We're showing how the electrons move. We are leaving those out in these two lower pathways. So we're just showing the reagents, not the mechanism. But this is how almost all of our nucleophilic additions upon carbonyls will work. We'll have some strong nucleophile, which we may need to make, and then that'll react with our carbonyl compound.